Part B, Problem B1. A platform is attached to the ground by an ideal spring of constant K. Both the spring and the platform have negligible mass. Assume that your mass is mp. Sitting on the platform is a rather larger lump of clay of mass mc equal rmp, where r is some positive constant that measures the ratio mc over mp. You then gently step onto the platform and the platform settles down to a new equilibrium position, a vertical distance d below the original position. Throughout the problem, assume that you never lose contact with the platform. Questions. A. You then slowly pick up the lump of clay and hold it a height h above the platform. Upon releasing the clay, you and the platform will oscillate up and down. You notice that the clay strikes the platform after the platform has completed exactly one oscillation. Determine the numerical value of the ratio h over d. B. Assume the resulting collision between the clay and the platform is completely inelastic. Find the ratio of the amplitude of the oscillation of the platform after the collision, AF, to the amplitude of the oscillations of the platform before the collision, AI. Determine a ratio AF over AI in terms of the mass ratio R and any necessary numerical constants. C. Sketch a graph of the position of the platform as a function of time with t equals 0 corresponding to the moment when the clay is dropped. Shown one complete oscillation after the clay has collided with the platform. It is not necessary to use graph paper. D. The above experiment is only possible if the mass ratio R is less than some critical value Rc. Otherwise, despite the clay having been dropped from the height determined in Part A, the oscillating platform will hit the clay before the platform has completed one full oscillation. On your graph in Part C, sketch the position of the clay as a function of time relative to the position of the platform for the mass ratio R equal Rc. Question A. You then slowly pick up the lump of clay and hold it a height h above the platform. Upon releasing the clay, you and the platform will oscillate up and down. You notice that the clay strikes the platform after the platform has completed exactly one oscillation. Determine the numerical value of the ratio h over d. So first let's write equation connecting distance d, big D, and other parameters. So we have kd equal mp multiplied by g. This is from our first assumption. And after that we can count that constant k equal mpg over d. Second thing, because we already know what is this equation, we can find what is omega for this oscillation. That will be square root from k over me. And now we can find the full period for this oscillation. This is the expression for full period. And for the same period, our clay start to fall down and reach the lowest point from where we start our oscillation. We did oscillation from lowest point somewhere to this lowest point. It means that our clay reached distance h for the same period of time. So we have this equation. From one hand we have h equal 1/2 gt square, and when we put t expression for period, we will have this expression, and after that we will put k as this relation, and we have finally this answer, h over d equal 2 pi square. Question B. Assume the resulting collision between the clay and the platform is completely inelastic. Find the ratio of the amplitude of the oscillation of the platform after the collision AF to the amplitude of the oscillations of the platform before the collision AI. Determine AF over AI in terms of the mass ratio R and any necessary numerical constants. First of all, we can find what is the new equilibrium position for the first oscillation, because this oscillation stop right in on a distance d. So first of all, we can count what is amplitude for the first oscillation before collision, because if this fellow reached the lowest point, it means that it has a maximum displacement from new equilibrium. But new equilibrium now we can find from a force of gravity which created by a piece of clay, because before the equilibrium position was right in this point, and now it must go higher on a distance, this one, where mc it's a mass of piece of clay, mg that's extra force of gravity. So it means that it must be equal to k multiplied by ai, where ai is this amplitude for this oscillation, because it's oscillate between lowest point and the point of equilibrium, which is higher on this distance ai. So from here we can count what is ai. This is the expression. So second step. Now let's see what happens when clay is hitting us in the lowest point. When it's hitting in the lowest point, it means that now we have the same mass as in the beginning. So it means that in the lowest point now is the equilibrium point for our second oscillation. And now we can count what is the total kinetic energy from this point, because this piece of clay hit us, and we can count what is total speed, initial speed in this position. For that we have to count first what is the speed of this piece of clay right before collision. This could be found from formula Vc square equal 2gh, where Vc, where h is distance traveled by this piece of clay before it hit this platform. So it means that Vc equal this expression. Now we have a completely inelastic collision with the platform, so we can count what is speed of platform right after collision. We just use momentum conservation. So previous momentum mc/vc, that was equal new momentum mc plus mp multiplied by our speed after collision. And now we can count what is this speed. That's this expression. And the last step is we can find what is total kinetic energy in this position and equalize it to potential energy of our oscillation in a point of amplitude. So we have this expression. This is our kinetic energy going to potential energy for spring with the amplitude with a new amplitude AF. Now we can count what is a new amplitude. We have this expression, and the amplitude, it will be this one. Now we can count what is the relation between final and initial amplitude. So we have to divide this expression by this expression, and we will get this formula. So we have to exclude constant k, but we remember that constant k was first found from this k equal mpg over d. So we can substantiate it here, and we have this expression. Also we have h over d we already counted. That was this one, and finally we will get this formula, and totally this is the our answer: 2 pi over root from 1 plus r, where r is coefficient between mc and mp. So that's the solution for question B. Question C. Sketch the graph of the position of the platform as a function of time, with the t equals 0 corresponding to the moment when the clay is dropped. Show one complete oscillation after the clay has collided with the platform. It is not necessary to use graph paper. So let's see. If we have a very small amplitude for platform oscillation, this graph looks like this, and we see that clay will never cross a platform before lowest position. But suppose that we have a big amplitude for this platform. So in that case we can draw this picture, and we see if for example if this parabola from clay cross this first time cross sine function from platform in top position, it must cross it again second time somewhere before it crossing third time in lowest position. Let's count what happened if this clay crossing platform in the highest position. Highest position, it means that platform moved for half period, and for this half period that was half time for clay to drop. It means that clay reach a height only 3 over 4 h, and if this is height 3 over 4 h, it means that amplitude for platform will be 3 over 8 h. But from other hand, we already counted that amplitude initial equal this expression, and the spring constant was this expression. And also for our case we had this relation. Now let's combine all this stuff. We can insert in this formula K and use relation H over D, so we will get this thing. So we have amplitude for a platform equal RD, and now we can equalize it to 3 over 8h. That will be this one. It means that R equals 3 over 8 h over d, but h over d equal 2 pi square. So finally we will get this answer. So it means that for a relation between mass of clay and mass of platform equal to 3 over 4 pi square, first time clay will meet a platform in the highest position. After that it will cross platform somewhere, and later it will meet in lowest point platform. So we see that for small amplitude, for very small relation between mass of clay and mass of platform, they will never meet before lowest position. For big rate they will meet 3 times, so it means somewhere between this parabola it will just touch this sine function, and that's a critical relation between mass of clay and mass of platform. So it exists.